Okay, so we're going to pick up where we left off. We talked about setting up the hypotheses, and now we're going to start evaluating evidence against the null / for the alternative. Do the steps, throw them back out. So you're going to state the question of interest, identify your parameter of interest, and take inventory. We're going to state our significance level. Choose it to be 0.05 if none is stated, but a lot of the time we will actually state a significance level, state the alternative and null hypotheses, check your conditions. If you don't meet these conditions, you have to change the test statistic and that you use to calculate your p-value. Calculate the test statistic and p-value, and then return to the question and answer it. And we have a format for that. We will go through it. So similar to standardizing, so it's going to be really similar to when we were calculating z-scores. A test statistic, and this is a generic phrase for test statistic. You can have a z test statistic, you can have a t test statistic, and so on. Compares what we saw in our sample, so this might be a sample mean, to a hypothesized our null parameter value, so whatever's claimed. So what we saw in the sample minus what's claimed over some amount of variability for that test statistic. So what we saw in the sample minus what's claimed, hence you remember from the null hypothesis, it had a 0. Well, that's that null value, so that's the claimed value, over the standard deviation for that test statistic. So here, we start out assuming the null is true. So given the null is true, what is the probability we would have seen what we saw in the sample or more extreme? Something that's further from the claim statistic that we saw. And this is a probability, and we have a special name for it. We call it the p-value. So the p-value is the probability that you see as or more extreme results as you did in your sample, given that the null is true and the parameter is equal to the value that's claimed. And we'll translate into that train example. So p-value is a probability. One thing to note, it can't go below 0 and it can't go above 1. If either of those things happen, that's a really good sign to backtrack and check your work. So making decisions, we calculate this test statistic, which we use to get a p-value, but then you have to decide what the heck you're going to do with that. A small p-value is very strong evidence against the null / for the alternative, because it's indicating, hey, if the null is true, what we saw in our sample is really rare, it's really weird, so maybe we don't believe the null is true anymore. That's the idea. If you have a big p-value, that indicates that, hey, what happened in your sample happens fairly often if the null is true. So you do not have good evidence that the null is not true. So we are going to, and this will be a very, very important concept. So if the p-value is less than or equal to this alpha significance level, so that's another Greek letter we're throwing at you, alpha, this is your significance level. And we'll talk a little bit more about it in lesson 25. But this significance level is set ahead of time. If your p-value is smaller than it, it tells you, hey, reject the null and conclude that the alternative is true. If you have a big p-value, so it's bigger than your significance level, we fail to reject. And we are very, very particular about that language. We fail to reject. We do not accept it. We fail to reject it. Very, very, very particular there. It's basically saying, hey, we do not have enough evidence to say the null is not true. We can't say the alternative is true here. So, handy little visual there that here's your alpha level. It's going to be between 0 and 1. Anything between alpha and 1 is going to be a fail to reject. Anything between 0 and alpha will be a reject. So, in addition to just saying whether or not we reject the null, we also want to talk about how strong our evidence is. So we will have a p-value, and we're going to want to, we have a spectrum here. Based on that p-value, do we have strong evidence? Like here, if it's between 0.01 and 0.05, we'd probably generally call it fairly strong. Right around 0.05 is where I'd call it moderately strong. And then there's this threshold, anything above 0.10, that's a huge p-value. We're never going to have a significance level high enough to reject there. It's going to be little to no evidence. You might also hear people call it weak evidence. And then if it's very tiny, like our p-value is between 0 and 0.01, most of the time we'll say, oh, this is very strong. Or you might even hear that this is convincing evidence that the null is not true. So things to note here, the smaller p-values are stronger evidence. Larger p-values, they don't really give us much evidence at all. Imagine it's like being a prosecutor and you just don't have evidence against the defendant. It doesn't prove that the null is true, but you were not able to show that the alternative was true. So things to note, the smaller your significance level is, the more extreme your results have to be in order to reject the null. And then, very important, we don't like to say we accept the null. We will totally jump on that every time we reject or fail to reject. So reject or fail to reject. Those are the only two terms that we like to use there. Do not throw it in a thesaurus. It will not mean the same thing. This is one of those cases, our language is so particular, you want to stick to it, I promise. So just like this, so we had that slide for the confidence interval write-up. You're going to want to flag this and have this written down somewhere as well. So we have a two-part, so here's first part, here's the second part, write up for a hypothesis test. The first part is where we say we reject or fail to reject and then you have to give us a p-value and a significance level. In some of my write-ups, I'll also include the test statistic as well. And then here, trust me, this last blank is probably deceptively small. In reality, you're going to need a whole other line. But here is where you use that spectrum. You say, hey, there is blank evidence. So like, there is very strong, moderately weak, little to no evidence to suggest. And then this is the one we'll need practice on. Here is where you state the alternative hypothesis is true, but you state it in words and you state it in context. So if I were talking about the train example, I'd say, hey, there is blank evidence to suggest that the average trip time for all train trips between Florence and Rome is greater than 94 minutes as claimed. So this is the one to really, really, really focus on. This is usually the one that people need the most practice on, is filling in that blank. So a z-test for a mean, so we're going to go through conditions where we're looking at the average value from a single population, and when we can use z procedures. So it's similar to using z procedures for the confidence interval. So we want to make sure we have a representative sample. Usually we're going to ask for a random sample. Based on central limit theorem, we know that the sample size is big enough. Central limit theorem is going to kick in. X bar, sampling distribution of X bar is going to be roughly normal. And then this condition is very specific to z procedures. So like if you want to use z procedures for a confidence interval and you have a z star for your critical value. Or in this case, we use what we call a z test statistic. You must meet this third condition here. Once you do, you set up your hypothesis. So this mu naught, it's a number. So this will be the claimed value. You will not actually write mu naught, you will actually write the value. and units, if there are units. So I'm going to include here. So like the train example, it's going to be this sort of scenario. So we're looking at a higher tail for our p-value. If our alternative was looking at lower, our p-value would be the lower tail. And if it's two-sided, then you have to look at both. So our test statistic here is a z-test statistic. It's going to be what you saw in your sample, so x bar, minus what's claimed, so mu naught, over sigma over root n, which is equivalent to over sigma of x bar. So we're going to talk about this test because it's simple and straightforward as far as the tests go. In reality, though, we almost never know the value of sigma of x or sigma of x bar. It is incredibly unlikely that we know that parameter value. Next week, we're going to delve into, well, what happens when we don't know it, that kind of idea. So we're going to go here, going to go through the steps for our z-test for the mean. So we're looking at the high-speed train. They advertise it takes 94 minutes. That's our value of mu naught. The times vary on average. That's our sigma of x. They decide to take 25 random rides. I hope they didn't actually have to sit through them. That could have been really, really long. This is my significance level. The average from their sample, so this comes from the sample. That's x bar. So there we are. Question of interest. I want to know, and for a hypothesis test, this question of interest should be expressed in a sort of yes or no format. So, is this true kind of idea? Is the average train trip time of all trips between Rome and Florence? That's my population there. And then what I'm interested in finding out, is it higher? Is it longer? Is it longer than 94 minutes? And you can write that as claimed. You can be more specific as claimed by the website, but it's really important that you put the 94 minutes in there. So my parameter of interest, I'm going to show you, like, this is my notation. So mu of x, because x is just train trip time from one ride. So the mean of all of them. So mu x, and that's going to be the mean train trip time of all trips between the two cities. Rome and Florence. So if we ask you for the parameter and we ask you for notation, that's what we mean. If we ask you to describe it in words and context, we mean the second part. Sometimes we'll ask for both, so that's good to know. So the claimed value is at 94 minutes. The mean from the sample 25, that was 99 minutes. My sample size was 25. I know my sigma is 10 minutes. And then, do I have... Okay, that's the key step right there. So then my hypotheses. It's a lot crammed onto one side there. So my null is going to be really boring. It's going to be just stating what the website claims. So mu, okay, so I'm talking about the population, is equal to what's claimed, so 94 minutes. the alternative, I'm still going to have mu, I'm still going to have 94 minutes. But then we're thinking, oh, consistently late, they're convinced the average time is longer, so we're going to look at greater than. So this is going to be a one-sided test. You can look through our conditions. Note that stating the significance, it might be on the next slide there. It's just a 0.05. That's right there. So was it, did we get our sample as a random sample? Yes, they randomly sampled those 25 times. Is n sufficiently large? Depends. Right, so our sample size is 25. So what we would want to do, and I don't believe we have for this particular side, we would want to look like at a histogram and or a box plot of the data and see if it's, as long as it's not very skewed, 25 will probably be big enough. But if it's roughly symmetric, if it's kind of normally shaped, absolutely 25 is big enough. If it is very skewed, 25 may not be. So keep in mind, we may not for sure have a big enough sample here. And do we know sigma? Yes, that was that 10 minutes. So then, see, sigma 0.05. You are totally, like, you can write significance level if you want. That's fine too. So test statistic and p-value. Let me double check, make sure. Ooh, okay. So I'm going to use a z-statistic. I was hoping I had a normal table on there to look at. So x bar minus what's claimed over sigma over root n. And hey, we have 25 as our sample size. That's pretty sweet. So 99 is what's observed, minus 94 is what's claimed, over 10 divided by root 25. Ooh, I like that. I like that a lot. I get 5 over 2, which is 2.5. So, things to consider. I'm probably going to use up more space than I want. If the null is true, it's going to be centered at 94, as claimed. And then we saw or observed 99. So our p-value should be 99 or higher. So we want probability x bar is greater than or equal to 99. That's the probability that z is greater than or equal to 2.5. I'll throw in the 0 there. So remember, if you're following along with the z-table, you're going to need to do that 1 minus bit. Probability z is less than 25 or 2.5. Let me see, what do I get here? Oops. I am running out of space. Sorry about that. It's getting really touchy. I'm just touching the screen and it's not liking it. I get from the z-table 9938, which is equal to 0.0062. So that's my p-values, 0.0062. What that means is if the average train trip time for all the trips between the two cities is 94 minutes as claimed, the probability that I would have taken a sample of 25 random times and got 99 minutes or longer as the average time, that only happens about 0.62% of the time. So less than 1% of the time that happens if it really was 94 minutes. Which is why we're like, oh, okay, well that barely ever happens. We don't think our sample's weird. So we actually, what we do is we end up rejecting the null. Small p-values, we reject the null. And I have a cute little p-value song I can post to Canvas that we put together in the department. So, oops, we reject the null hypothesis with a p-value of 0.0062 at the 0.05 significance level. So here you could say there is convincing, very strong is okay as well. There's very strong evidence to suggest that, and now I have to state the alternative in words, in context, so that the mean train trip time for all trips between Rome and Florence is higher or longer. Either one is fine, but longer than 94 minutes. So you can add more, like you can say it's longer than the advertised 94 minutes, whatnot, but it needs to have that 94-minute value in there. So our first part, we say whether or not we reject and why, because this p-value is what we got at this significance level. And then our second part is we say how strong the evidence is for the alternative in context. So there's convincing evidence to suggest the mean train trip time for all trips between Rome and Florence is longer than 94 minutes. So I just wanted to leave y'all with a few notes. I know it's kind of like a little eye-rolly, but we do emphasize we don't ever accept the null. We reject it or we fail to reject it. So there for you. I didn't even make this one. You'd be really surprised how many stats memes are out there. But the analogy that we're going to try and use to communicate this across. So in the U.S. court system, supposedly the system is supposed to be presumed innocent until proven guilty, right? So we would even say, okay, the null hypothesis is the defendant is not guilty. The alternative is that they are guilty. What the bottom line is here, so suppose you don't reject the null hypothesis. So the defendant is found not guilty. We are not quite sure. You want to definitely ask yourself, is this the same as proving someone's innocent? Right? So a not guilty verdict, it could be that the person is innocent. However, it could also be that, it could be that there was not enough evidence to convict a guilty person. So when we fail to reject the null, we don't know which it is. We don't know if we failed to reject the null because the null is true, or if we just didn't have strong enough evidence. So that's why we don't accept the null. We just reject it or fail to reject it. And that's the logic behind that. I like to kind of joke, one way to think about hypothesis testing. So you may be familiar with the meme, you may not. So change my mind guy. They are sitting there at their table. They believe the null hypothesis is true. Change my mind. So you walk up and you do. You try to, you give them evidence. You try to change their mind. However, at the end of the interaction, they don't change their mind. This does not mean they're correct. It could mean it is true that they could be correct, but it's also possible you just didn't have strong enough evidence to change their mind. So that's what it comes down to, is hypothesis testing. It's like assuming, change my mind guy assumes the null is true, and you have to try and convince them otherwise. You either do convince them and they go, okay, yeah, the alternative must be true, or you fail to convince them, in which case it doesn't prove they're right. It just, you haven't demonstrated that they're wrong. I know, we're it sounds very cynical, but that is how we work here. And then just a couple notes on p-values. So the p-value talks about how strong our evidence is in terms of for the alternative. You could also think of it as against the null. When we do our write-up, we usually try to say there is blank evidence, and then we write for the null, or sorry, for the alternative in context. Trust me, it's a lot easier than saying against the null here. You end up using a lot of double negatives. It gets really gross really fast. It's very difficult to understand. So just stick to the format that we have. There is blank evidence for the alternative in context. The smaller the p-value, the stronger the evidence for the alternative. The larger the p-value, the weaker the evidence is. And then we have this term, and it's not the end-all be-all that a lot of folks think it is. Statistically significant. So if somebody says something's statistically significant, that means that it's different enough, like the p-value is small enough that they rejected the null. It literally is just a key term to say, I rejected the null. My p-value was small enough. It indicates the p-value is less than the significance level. And if you get statistical significance, great. We'll hint at something called practical significance. It's really great to have both because you can have just one or the other, and it's a lot more complicated when you do. Okay, so that's lesson 24, and we're going to talk about those conclusions, errors, and cautions. Specifically, I was just poking at a caution. So we'll see you there.